Hi everyone, in this video segment we are going to harp on this idea of irreversible versus reversible acid-base reactions, as this is a really important concept. It will come up later in the course and be pretty consequential. So we're going to consider two acid-base reactions, one between a terminal alkyne and NH2 minus, and one between our terminal alkyne species, so same acid in each reaction, and hydroxide, okay? So the acid-base arrow push would be the same for each of these. NH2 minus will share a pair of electrons with the proton bonding to it. We break the carbon-hydrogen bond, leaving a lone pair on the carbon. We create our conjugate species, which would be your acetylide ion, that's the name of this guy, and you have NH3 neutral. In the bottom acid-base reaction, we have hydroxide deprotonating the terminal alkyne. The conjugate species would be water, and again, our acetylide ion. Now, we're going to calculate KEQ and use the approximation that we did in our last video to figure out, are these reactions product favored or are they reactant favored, and to what extent is it product favored or reactant favored? So we're going to use the pKa value 26 for the terminal alkyne. Some resources say 25 or 26. We're going to go with pKa 26. So the pKa of the reactant side acid is 26. The approximate pKa of ammonia, NH3, is going to be 36, and the approximate pKa of water is around 16. Now, resources will say it's 15.7. I'm going to round up to 16 for the sake of this calculation. So if we were to calculate KEQ for our top reaction, we would take 10 to the pKa of the product acid, 36, minus the pKa of the reactant acid, which is 26, and we get 10 to the 10. Okay, KEQ is approximately 10 to the 10. The KEQ of the bottom acid-base reaction between hydroxide and your terminal alkyne. We're going to calculate it. 10 raised to the pKa of the product acid, 16, minus the pKa of the reactant acid, 26, and here we get 10 to the negative 10. Okay. Now we said before that if KEQ is 10 to a positive integer, that meant the reaction was product favored. So at the very least, we know that this top reaction is a product favored acid-base reaction. Okay. We said in the former video that if KEQ is 10 to a negative integer, then that reaction would be a reactant favored acid-base reaction. Therefore, we know the reactant side is actually favored at equilibrium when we look at the acid-base reaction between hydroxide and the terminal alkyne. Now, let's think about irreversibility here. We also said that if KEQ was 10 to a value of 3 or more, okay, there would be an irreversible acid-base reaction. Because this top acid-base reaction between your terminal alkyne and NH2 minus has a KEQ of 10 to the 10, we could say that this reaction is irreversible. Okay, it's an irreversible acid-base reaction. NH2 minus will rip off this proton. It will deprotonate the terminal alkyne to make these two species. And the reverse reaction of the acetylide ion deprotonating to form these two is so infrequent and statistically less likely to happen. Not only is it less statistically likely to happen, it's energetically not as likely to happen. Okay, this side is favored at equilibrium, the side with the higher pKa acid. It is the more stable side, and at equilibrium, that side is favored, and we could consider this acid-base reaction between these two species as being irreversible. However, if we considered the bottom acid-base reaction, when OH minus deprotonates, what would then happen from a stability standpoint is that the acetylide ion would rip off the proton from H2O and form these two species again, okay? And this side is favored. So if hydroxide does take off the proton to produce these conjugate species, what's happening is that the acetylide ion would very quickly take back the proton from water to reform hydroxide and the neutral terminal alkyne. And that would be very, very much favored. In fact, because of the difference in the pKa values, right? We're saying that at equilibrium, we have a whole lot of this. There is a lot of this, that this acid-base reaction to form the acetylide ion is statistically insignificant, okay? Meaning at equilibrium, there is like, I don't even know the exact value, but a very, 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 very small percentage of the acetylide, whereas at equilibrium up here, there's approximately 100% of the acetylide ion because of the irreversible acid-base reaction. So again, we have this idea of irreversible acid-base reactions being important in organic chemistry. And we could say that, let's make a statement, if you have an acid, to have it irreversibly deprotonated by a base, that base needs to form a conjugate acid species whose pKa value is at least 3 values greater than the pKa of the acid that we're trying to deprotonate. That's what we did here. We basically calculated the KEQ and said there was a difference of 10. So yes, it's greater than 3. Therefore, yes, this base is strong enough to irreversibly deprotonate to form our conjugate species. However, that was not the case down here. Hydroxide would deprotonate to form a conjugate acid whose pKa was smaller than the pKa of the acid we were attempting to deprotonate. And as a result, the reverse reaction was more favorable, and it was a reactant-favored reversible acid-base reaction. It was not irreversible.